All right, let's jump right in. Picture a modern smart city for a second. We're talking a massive cinematic skyline, just buzzing with drones, constantly monitored by thermal imaging, and managed through incredibly complex digital models. And right at the absolute center of this high-demand, super tech-driven landscape, that is the building surveyor. You're the guardians of safety, compliance, sustainability, and asset management in modern infrastructure. It doesn't matter if it's a towering commercial skyscraper, a delicate heritage conservation project, or a massive industrial plant, the surveyor is the professional making sure the built environment actually works the way it's supposed to. And because of rapid urbanization, the international demand for these pros is literally skyrocketing. We're talking top-tier salaries because the industry desperately needs leaders who can navigate these complex, high-stakes environments. So in this explainer, we're going to walk through the complete professional syllabus that takes you from a novice to an absolute master in this globally demanded field. To really grasp why this role is so absolutely crucial, we have to look at the environment surveyors actually operate in. The whole engineering, architecture, and construction lifecycle, it is notoriously complex and packed with risk. I mean, former MI5 Director General Stella Rimington once noted in her autobiography that dealing with the building industry was just as tricky as dealing with the KGB. It's a massive, high-stakes arena with countless moving parts, competing interests, and so many unforeseen variables. The surveyor's fundamental job is to cut right through that chaos, mitigate those risks, and bring order, safety, and legality to the whole project. So here's the roadmap for our explainer today. We'll be moving through 5 core areas: foundations, instrumentation, pathology and structural health monitoring, legal frameworks, and finally global standards. Starting off with Section 1, Foundations. Before you can master the high-tech tools of the trade, you need a rock-solid grasp of these prerequisite skills. These are your non-negotiable core competencies. You simply cannot diagnose a structural failure if you don't understand the basics of reinforced cement concrete, or RCC, and steel structures. You need sharp math skills too, specifically trigonometry and coordinate geometry, to handle areas, volumes, and error analysis. On the digital side, a working knowledge of computer-aided design and building information modeling, or BIM, is absolutely essential for navigating modern site data. And honestly, perhaps most importantly, you need the soft skills: site communication, safety principles, and technical report writing, because the surveyor's findings are completely useless if they can't be clearly documented and communicated to clients and contractors. Let's move right into Section 2, Instrumentation. This is where the digital revolution meets the dirt. Surveyors today, we are effectively data scientists in hard hats, relying on a vast array of modern tools. We're talking about total stations and differential GPS for high-precision measurement. We use laser scanners for capturing real-world spatial data, and thermal imaging to see what the human eye literally cannot. Field data management is entirely electronic now. Surveyors use NEZ auto-calculation, which stands for northing, easting, and zenith coordinates, along with P-code libraries, to make sure all that complex data flows seamlessly and efficiently from the field right into the office software. And this perfectly highlights the level of extreme precision we're dealing with. When you're using GPS, you are relying on a constellation of satellites orbiting at a staggering 20,200 kilometers above the Earth. But it's a bumpy ride up there. Satellites are pushed and pulled by the non-spherical shape of the Earth's gravity, tidal forces, and even solar radiation. This actually creates an error in the satellite's broadcast ephemeris known as orbital bias. A master surveyor has to understand these physical biases and how government control segments constantly track and correct them, just to ensure that millimeter-level accuracy you need on site. So the crucial point is knowing where and how to apply these tools, because depending on the environment, your methods change completely. Topographical surveys are land-based. You're mapping out the surface features for site planning. But if you're working on a harbor or coastline, you transition to hydrographic surveys. That's water-based mapping. Here, the surveyor drops the laser scanners and instead busts out echo sounders and sonars to measure water depth and map out hidden navigational hazards beneath the surface. It's a completely different skill set under the exact same profession. Moving on to Section 3, Pathology and Structural Health Monitoring. This is all about diagnosing the health of a building. Building pathology takes a holistic approach to investigating failures, very much like a medical doctor diagnosing a disease. Defects basically fall into 2 categories. First, patent defects. These are the ones you can find with a reasonable visual inspection, like a massive obvious crack in a wall. Latent defects, however, are hidden. Think foundation settlement or internal corrosion. To find those sneaky latent defects, surveyors use non-destructive testing, or NDT. Tools like rebound hammers and ultrasonic pulse velocity allow us to literally look inside the concrete and evaluate structural integrity without doing a single scratch of damage to the building itself. Now, historically, the industry relied heavily on time-based maintenance, replacing or repairing parts on a fixed schedule regardless of whether they actually needed it. But through modern structural health monitoring, we are shifting to condition-based maintenance. And this is a total game changer. It means we monitor the actual, real-time, physical response of the asset, and we only deploy maintenance budgets when the data tells us a defect has actually been detected. It minimizes downtime and drastically reduces those massive inspection costs. Let's break down how this workflow builds using Ryder's 4 levels of structural health monitoring. This is the absolute gold standard. Level 1 is simple detection, just identifying that a damage event has occurred. Then Level 2 is location, pinpointing exactly where that geometric defect is. Moving deeper, Level 3 is assessment, determining the severity of the damage. And finally, Level 4 is prognosis, taking all that data and predicting the remaining service life of the asset. As you ascend from Level 1 up to 4, the complexity of the data processing required increases significantly. To achieve these 4 levels, surveyors deploy advanced sensor networks. Passive sensing is exactly what it sounds like. Sensors just sit quietly and monitor the environment or operational conditions, waiting to pick up a signal. But active sensing is much more dynamic. Active systems use transducers, like piezoelectric sensors, to actually inject controlled diagnostic signals, such as guided lamb waves, directly into the structure. By measuring how those waves change as they travel through the material, we can actively interrogate the structural condition and pinpoint local defects with incredible accuracy.
That brings us to Section 4, Legal Frameworks.
Because diagnosing a building is really only half the job. Administering the contracts and managing the legal risk is the other half. Construction projects are bound by highly complex legal agreements, and surveyors must be fluent in industry-standard forms of contract, like FIDIC, JCT, and NEC. You are responsible for contract administration. This means auditing work progress to authorize interim payments, managing extra work variations, evaluating extensions of time, and deeply understanding your strict professional duty of care. If a surveyor acts with negligence, the professional indemnity and liability consequences can be absolutely severe. Just look at this number for a second, 12.8. That is the average number of months it takes to resolve a construction dispute in the UK. And astoundingly, the UK actually resolves them faster than the global average, and it still takes over a year. Furthermore, the average value of these disputes is nearly $18 million. This perfectly highlights why proactive surveyors, the ones who can manage risk, avoid variations, and keep projects out of the courtroom entirely, are so incredibly valuable to employers.
But hey, sometimes standard mediation fails on these massive, complex projects. When that happens, parties often turn to arbitration. Global entities like the International Chamber of Commerce step in through their International Court of Arbitration. Now, they don't make the formal judgments themselves, but they administer the arbitration, providing judicial supervision, appointing independent arbitrators, and scrutinizing awards to ensure they are actually enforceable. A high-level surveyor has to know exactly how to navigate these tribunal environments, and even provide expert witness evidence when it's required.
Finally, we arrive at Section 5, Global Standards. If you want to work globally, you must speak the global language of compliance. This is your ultimate rulebook. Depending on where you operate, compliance is not optional. It is the law. In India, a surveyor relies heavily on the National Building Code, the Bureau of Indian Standards, and CPWD guidelines for everything from fire safety to environmental regulations. But on the international stage, you'll be cross-referencing with standards like the ICC International Building Code, OSHA for worker safety, and guidelines from the Royal Institution of Chartered Surveyors. A master surveyor knows how to synthesize all these codes to ensure that a building is legally viable from day one. And beyond basic safety, today's surveyor is also a sustainability auditor. We evaluate energy performance to meet standards like the U.S. Green Building Council's LEED rating system. This holistic framework requires checking prerequisites and earning points across water use, materials, and indoor environmental quality. Hit 40 to 49 points, and you are certified. Silver is 50 to 59, gold is 60 to 79, but if you want to prove true sustainability leadership and hit platinum, you need 80 points or more. Guiding a project to these milestones is a massively in-demand skill that commands top-tier compensation. We have covered a massive amount of ground today, from the fundamental trigonometry of a foundation to the laser scanners in a drone, right up to the legal halls of the ICC. The built environment is evolving faster than ever, demanding professionals who are part engineer, part data scientist, and part legal scholar.
So the question I want to leave you with is this. Armed with this comprehensive syllabus, how will you step up and apply this mastery to shape the future of sustainable, safe, and resilient global infrastructure? Thank you so much for joining me on this explainer, and I really look forward to seeing the world you build.